Hi, this video is all about POCASA, Power Off Circuit or Component Analog Signature Analyzer. First off, I'm not a professional video blogger by any stretch of the imagination, nor do I have professional equipment. I've got a Logitech, who knows what webcam that is. I got a Logitech webcam sitting on the back of my laptop, a cheap whiteboard with a couple of gouges in it, and a bunch of fluorescent lights. That's all I got. But at least I made an outline of what I got to say. So, dig into it. First thing about POCASA, it's all about what you see. It's all about visualization. If you hook up to a test point on a particular circuit and you take a picture of that circuit, or whatever the screen might look like, here's your screen. Maybe that circuit looks like this, and you take a picture of another circuit and it ends up looking like that. You know something is different between the two because that one's a circle and that one's an ellipse. There's something different between those two. If you know this circuit works and this one doesn't, well, there's something wrong going on here. That's the whole thing. This POCASA doesn't care about volts, amps, ohms, henries, farads, mahos. What's a henry's backwards? Unirads, which is the inverse of a henry. Derefs, which is the inverse of capacitance. Doesn't care about any of that. All it cares about is the picture. Now you can infer all those units of measurements, but you don't need to. Again, you just care about the picture. So, the original POCASA was going to be powered by an ATX power supply. Give me plus 12, minus 12, plus 5, minus 5, plus V 3.3, plus 5 hot, plus 5 switch to all these different voltages. Because I thought I needed amperage to do all this testing. Turns out I don't need all that amperage. I can run it off a single USB port pulling no more than 500 milliamps. So that being said, I get my 5 volts off of my USB directly. That powers a LP 2950 for my 3.3 volts linear regulator, so I'm getting a little bit of loss there, it doesn't matter. I'm running that plus 5 volts through a PN Mini. If you Google PN Mini, you'll come up with a Kickstarter, which will take you to, I believe it's speedinglabs.com, and it's this little circuit. That one right there. Well, tiny little, about 1 inch square by 1 inch, or 1 inch square circuit that basically takes a positive voltage in, and if you configure right, you get a negative voltage coming out. So it's an inverter. That's where I get my negative 5 volts from. The LN, I've got an LM337 in there, which I power from my negative 5 volt to give me a negative 2.5 volt rail, which is used on the analog or the digital analog switching multiplexer switches, the ADG1406 and ADG1408. If I need more power, I can easily power this off a 5 volt wall wart, or I can parallel a couple of USB connections if I find that I'm needing more amperage to drive all this. But as it is, it's much simpler this way. The way I had it before was an ATX power supply input, a bunch of load resistors here, regulator here, regulator here, regulator there, regulator everywhere, regulator. Anyways, and a whole bunch of filter capacitors, these big old filter caps. Don't need all that now because I'm running it directly off 5 volts. And I think I hooked up a current monitor once, and the most I saw was 260 milliamps, or give or take 5 times 260 milliamps. So what is that? That's just over a watt, I believe. So nothing to it. Doesn't draw much at all. You can easily be driving off a LiPo pack, and with a suitable boost converter, driving that 3.7-ish nominal voltage up to 5 volts, and then from there inverting it back to your negative 5 rail. The MCU, okay, so the PSU, and you probably can't see this over here, but I'm not going to be writing much anyway. PSU is USB plus PN Mini. Yeah, and a couple of linear regulators for the lower voltages. As I say, the plus 2.5, minus 2.5, the plus 3.3 rails for the pick, and a handful of the other logic chips on here. The MCU in this one is going to be, or is, a PIC18F47J53. It's got a built-in USB port on it, 128K of flash, and 4K of RAM, along with the requisite other timers, analog digital converters. I believe this one's got a temperature diode and an RTC in it. I can't remember, but I'm not using those, so I don't need them. As it sits right now, I'm using about 100K out of this 128K flash, and I'm using all of the SRAM on there for variable storage, etc. And I'm running it at 48 megahertz because I've got it hooked up to USB. You got to be running it at 48 megahertz to do that. The core is running 48 megahertz, as well as the USB side of the house. My DDS chip, my signal generator chip, is an AD9833. SPI control, SPI bus control. Got a 25 or 24 megahertz master clock, meaning it can generate frequencies from 0 to 12 megahertz. It can generate a sine wave, triangle wave, square of, I don't know where I'd want to use the square wave, but it can make it. It's got a 10-bit DAC with a 24 megahertz crystal on it. I get about, if you do the math, you get about 0.1 hertz resolution out of it. And again, SPI interface, very simple chip. It comes in a, where is it, right there? Wait, that's in, what is that, a SO8? Or no, SO10, or MSOP10 package. So very small package. It's right above my fingernail right there. Tough to solder, but it's in there. So anyways, I take my AD9833 chip. We'll just say that's my, that's called a DDS chip, direct digital synthesis. I run that out, and I run that through a op amp. That's my resistor, in case you couldn't tell. And the DDS chip has a 0 to 0.65 volt output. Depending on your, well, it's almost always 0 to 0.65 volts. Again, sine wave, triangle, square wave, what have you. I ran that through my op amp, and I give it a gain such that my output is close to my plus minus 5 volt rails. The op amp runs at plus 5, minus 5 volts rail, a dual rail power supply, positive and negative. So that the output waveform here is pretty close to plus and minus 5 volts, whatever the op amp. Normally you can't drive it all the way to the positive rail, you can't drive it all the way to the negative rail, so I try to keep it symmetrical and try to keep it as close as I can to it. From there, I go to a digital pot. That looks more like an inductor, but it's a digital pot. Trust me, it's a digital pot. And I attenuate my input signal. I drive it to the maximum, and then I attenuate it back down. Before I was trying to control the loop gain of a subsequent op amp stage, and that introduced a whole bunch of problems. So don't do that no more. Down here, I got plus 2.7 volts, minus 2.7 volts. In here, goes through a resistor, through another digital pot. Yes, that's a digital pot. I know it looks like an inductor, but it's not. Through resistance, Basically what I end up here with is this is my summing node. This is the DDS output, my amplitude, and this here is my offset adjustment. This is going to move it above and below 0. Now if I get to a point where I've got my full output here and I try to move it all the way above 0, let's just say that at this point it's like this, it's equal above and below 0. Well, that's not too equal, but you get the point. And let's say I just try to shift it all the way above. I've already got maximum 5 volts here, minus 5 volts here, but I try to shift it all the way up. Well, you know, it wants to go from 0 to 10 volts, but it can't because the op amps are only running at 5. So what I end up with is clipping. You end up with a clipped sine wave that's real distorted, and it just, you don't want to do that. So that'll be taken care of in software control once you get the whole thing characterized. So your signal level and your offset goes to a summing point right to here, to which I AC couple that into a unity gain, just basically a buffer op amp, which is able to provide me with a little bit of power. These op amps over here, well, you know what? There's supposed to be an op amp right here, which is just a follower. This is just a unity gain follower down here. So pretend there is. That's all I got to say about that. Let me find my diagrams. Yeah. And as well, there's going to be a unity gain op amp right here too. Yeah, bad description, but if you got a pot, you're going to want to buffer it. If you got a pot, you're going to want to buffer it, so you don't mess with the following stages, gains and resistances and feedback loops and whatnot. So anyways, I got all this. I get my signal level coming out here, and that is again 10 volt maximum swing, +5, -5, and if you reduce the total, the peak to peak, you can shift it above and below 0 to get your various types of test signals. If you want it all the way above 0, if you want it totally positive, if you want it totally negative, you can do that. Otherwise, just stick with symmetrical AC signal coming out. +5, -5, +2, -2, what have you. So, we go on from that, get that erased. Now that we got our signal coming out of the DDS section, it's going to go into a resistance, basically a source resistance, or in this case, since it's AC, a source impedance node. You got a signal coming in, and you know this marker's just getting worse and worse. Should have bought a new one. This is my 80G1408 or 6, 1408, and it's a digital analog switch. Selects one of 8 channels. So I got my input going into here, and got an output coming out here. But each one of my outputs goes through a certain resistor. I'm only going to draw 3, and they're all connected together. This one here might, let's just say that might be 10 ohms, and that might be 25 ohms, and this might be 50 and 100 and 2. You know, it might be a 1, 2, 5 scale, just like oscopes are set up. I don't have it set up that way, but that's just what it might be. So let's just say if you have a 5-volt signal coming in here, it's going to go through 10 ohms. That's going to limit you to half an amp. You have 5 volts going through 50 ohms. That's going to limit you to a tenth of an amp, 100 milliamps. That's called your source resistance, and that comes into play down the road here. So this is my DDS input, DDS input, and this is the DDS that goes to the DUT, DUT, device under test. And this is where it gets interesting, I guess you could say. Well, once I have the source resistance, we're going to call it source resistance RS. This is ground. These are my 2 test points. Now I'm going to hook up a resistor of unknown value here. Let's say, for argument's sake, that I've got 10 volts going in here. This is 5 ohms. It's a really bad omega signal. And this is also 5 ohms. And just assume that I've got a DC signal going through here. It's not AC. At this particular moment in time, when I got 10 volts going through here, half the voltage is going to be dropped here, and half it's going to be dropped here. So what I do is I measure here and here. And what I get here is the voltage across the device under test, which in this case would be 5 volts. What I get here is 10 volts. Yes, it is 10 volts. It's always going to be 10 volts. This is always going to be what the input is. But what makes it work is the fact that this minus this voltage is going to be 5 volts across 10 ohms. Gives me, what is that, half an amp, right? Yeah, 0.5 amps. And that's where you get the VI curve from. You get 5 volts, half an amp. If this goes down to, say, 1 volt, 5 ohms is still 5 ohms, you get the same. you'll get 0.5 volts here, and you get 0.05 amps here. 500 or 50 milliamps versus 500 milliamps. What that does for you on your picture, if you have your X and your Y, your X is your voltage and your Y is your current. As your voltage here goes up, so does your current up there. So your characteristic trace of your resistor is going to be this slanted line, and in this case it's actually going to be a 45-degree line, because you're well, who knows if it's going to be a 45. It depends on how you scale it well, how I scale it in my software. It's going to be this line right here. Now let's just say that I change this to 50. We'll go with 45 ohms. Makes the math work out nice. 50 ohms total. We're going to go back to 10 volts. I'm going to drop 9 of my 10 volts across here. 9 volts. 10 minus 9. And again, you do this part in software. You subtract this from this to get your current. This minus this is going to be the current flowing across here. Simple Ohm's law or Kirchhoff's law, or one of those guys' laws. I'm not a lawyer. So you get 1 volt over 50 ohms total. 50 ohms total here. 1 divided by 50 is 20 milliamps. Better be. Yeah, 20 milliamps. So at that same 10 volt signal, at that same spot, let's just say that before it was up here, I'm going to be getting 10 volts over here, but instead of 5 volts, I'm only going to get 1 volt. So my line might be down here somewhere. It might be almost horizontal. And that's what this does for you. The picture, if it's a horizontal line, it's more open. If it's a horizontal line, the device under test is more open than the source resistance. And you'll see that in a minute when I take this device under test out completely and when I short it out completely. A vertical line is more shorted just because of the way the math works. In fact, I'm going to go ahead and do that now. Let's redraw this here. And I hope you can see this in my wonderful lighting here of my shop. Can't, don't worry about it. If you don't get it, you'll get it one. If a person doesn't understand this or get it or why this is useful, I guess you almost have to see it in action to figure out, hey, that's cool, you know, that kind of thing. So now we've left our device under test terminals open. So 10 volts coming in again. 100 or 10 ohm source resistance. We'll just make it work out real nice like that. 10 ohm source resistance. The voltage right here is going to be that voltage. Infinite ohms here. Ohm's law again. You're going to read 10 volts here. You're going to read 10 volts here. 10 minus 10 is 0. No current is flowing here. So be 0 volts, or rather 10 volts at 0 amps. Now let's swing that back to minus 10. You have minus 10 volts here, minus 0, minus 10. 0 amps. Remember, amps are here on the vertical, voltage is on the horizontal. You get a horizontal line, like so. Now, let's short this out. Now, Ohm's law, you get a short here. All the voltage is dropped across this resistor. Nothing is dropped across here because it's a dead short. 10 volts minus 10 volts minus 0 volts is 10 volts. 10 volts divided by 10 ohms. Ohms is 1 amp. So 0 volts, 1 amp. And again, to scale, you gotta kind of visualize this a little bit. Now let's drop that back down to negative 10 volts. Negative 0 volts here. 10 minus negative 0 is still 10, divided by 10 ohms is negative 1 amp. Vertical line for a short. So if you get this thing hooked up to a couple of test probes like this, or you got a couple of test leads out here, and you got them hanging just out in the wind like this, not touching each other, you're going to get a horizontal line. Open. Touch them together, they're going to short, and it's going to go vertical for a short. Anywhere in between means any other signature other than a completely vertical line or exactly vertical line or exactly horizontal line is something other than a wide open or a dead short. And I guess I got to say that's kind of relative too, because say you have a 10 meg resistor here, and 10 meg is nothing in some circles. 1 meg is, or 10 gig or 100 giga ohm resistor is nothing in some circles, but it's still going to be a little bit of current flowing through there. But you'll see either a horizontal line, even though there's a 100 gig resistor there, you'll still see a horizontal line on this thing, just because that's the nature of the beast. I'm not looking to get that last 1% or 5% or even 10% accuracy or readability here. This is just for general purpose for the average schmo. Dead shorts, same way. If your source resistance is 10 ohms and you've got a shorted resistance of 1 ohm, yeah, you might see it not be perfectly vertical. It might be over here. But if your source resistance is, say, 1,000 ohm or 1K, and you've got a dead short of 10 ohms. 10 ohms and 1K really ain't a lot. That's 1% of the total. So it might be just a hair tipped over, maybe. You might see it, you might not. Same thing goes if if you're looking on the milliohms or microohm scale. You won't see milliohms, you won't see microohms, but you will be able to see when you take those two probes and you touch it. Oh, that's a short, or something really close to a dead short. And then you can crank up your source resistance and you can see, well, how much of a dead short is it? Because if you've got something here that's, say, let's go with 1 milliohm, 0.001 ohms, and you turn your source resistance way down to, say, 0.1 ohm, well, now that 0.001 is a little more of 0.1 than 1 milliohm is of 10 ohms, and so on. So you dial this way down, you'll start to see a dead short of 1 milliohm. You'll start to see those differences. Let's throw a little diode in there. And we're going to stick with 10 volts. And I'm going to go ahead and stick with 10 ohms here just to keep the math simple. I think my marker's just about had it. Maybe not. Okay. That's a rotten diode. Okay, so as everybody knows, the diode passes current in one direction, totally blocks it the other direction. So our AC signal is coming in here. Here's our AC signal, whatever, there's 0. It's going to pass it on this side, on the positive side. It's going to block the bottom side, or the bottom half of the wave, the negative side. But it's only going to start passing once you pass the forward voltage of the diode. So we'll just say, for argument's sake, that this one here is your quarter volt, your silicon diode, I believe it is, 0.25 volts, give or take. We'll just say 0.25 volts. VF equal 0.25. So what you'd see on the scale, or on the output here, and I've shown this in one of my other POCASA videos. It's a terrible crosshatch. What you see on the POCASA videos is, as long as you're under VF here, it looks like an open. So your voltage increases to, we'll say, 0.25 volts here. It's still going to be open, except for maybe a little bit of leakage. And when I say a little bit of leakage, I mean a very small amount of leakage. And then it's going to turn into a short, but a short that's offset by your forward voltage. So as your wave goes positive, you'll get to a trigger point here, where it'll short out, if you will, and then start displaying an increasing voltage along with an increase or an amperage that's constant. And as you go back down the input wave here, it'll cut back off, and go to an open, and your wave will come back out this way. So basically you got this L-shaped, backwards L-shaped looking thing. Now let's switch that and let's go to a germanium diode, which I believe is 0.6 volts. We're going to leave our old this one up here, the 0.25 volt diode, for reference purposes. Now your voltage is going to increase, but it's going to have to go up higher to kick on the diode. So it's going to go over, saying like here, and then come back down, and it's going to come back down to about 0.6 volts, and it's going to shut off, and it's going to open up because it's going to be blocking all the current. And again, just to show how it works here, 0.6 volts. You got 0.6 volts across this point. You got 10 volts coming in here. 10 minus 0.6 would be 9.4 divided by 10 ohms, 0.94 amps. You're right. Yeah, that's right. Not that I'd ever use that much, because my source resistance is never going to be down around 10 ohms, just because parts can't handle that much current. But at 0.94 amps, that's up here at 0.6 volts. 0.94 at 0.94 in the eye, 0.6 on the volts. I come back down to say negative 10 volts. Well, the diode's blocking now. Diode's blocking, so it's going to be 0 volts across here. 10 minus 10, wait a minute, minus 10. Yeah, 10 minus 10 is 0. 10 minus 10 is 0, 0 amps. So no matter how far I go backwards on the negative voltage, I'm still going to have 0 amps. That'll be the curve. I don't know if I want to get into the diodes, because that's just, without a good visual, it's tough to see on paper, if you will. But it does work. A capacitor causes a phase shift in the voltage and the current. So let's just start from point 0. I'm going to throw 10 volts at this thing through this 10 ohms, and this capacitor is discharged. Initially, this capacitor is going to be a dead short, meaning you got all the amperage with no voltage. As the wave progresses through, the capacitor is going to charge up, which means its voltage, this point right here, is going to go up, which is fighting the voltage across here, which means its current is going to go down till you get to the top of the wave. Now, as the wave starts to drop, the voltage on the capacitor is going to drop, but the current's going to increase in the other direction. And now we're back here at 0. The negative voltage is going to go up, but since it's capacitor, it's discharged at this point, again, just like it was up here, but now it's got a voltage going the other direction. So you're going to be at maximum current with a decreasing current, but an increasing voltage, because that's what a capacitor does. And then you get to this point right here, down here, the wave reverses, or starts to reverse itself, starts to decrease in amplitude. Your voltage goes down, but your current goes back up. So capacitor is generally a nice circle. And with all these examples, you can throw in all sorts of stuff. In the diode, you can throw in leaks. A leaky diode might have a nice forward bias, but the reverse bias might show a little resistance in there. If you got a capacitor and a diode in there, you'll end up with what I call a golf club looking signature, something like this, because the diode starts to conduct up here. Here we go, something like this. The diode conducts up here. Once the diode switch on, it's a diode, but once the diode switches off, as in you start to come backwards, you get a golf club looking thing, because it's kind of like a capacitor back here. If you got a capacitor and a resistor, you'll get an oval, but it'll be tipped over like that, or an ellipse, but it'd be tipped over because it's leaky. Yeah, diode if it's leaky. If you got a bad diode, it'll either show up as a short or an open. If you got a capacitor and a diode in parallel like this, but it's a circle, then you know the diode is open because it's not doing you any good. If you got a capacitor and the diode in parallel and the diode is, the capacitor is totally blown out, then you're going to have a straight up diode signature. Because, jeez, this marker's about done, ain't it? Because the capacitor is out of the circuit. It's not doing anything. If the capacitor is shorted, well, then the whole circuit is shorted and you'd have your vertical line again. So, that's how that works. And on here, I've got an SRAM chip right there, 256K byte SRAM chip. What I do is, through this ADC here, I take these readings as fast as I possibly can, store them in the SRAM, and then dump them back to a PC over the USB port. And I'm getting something around 11,000 to anywhere between 11,000 and 14,000 samples per second. It could go a lot quicker than that. I'm doing a bunch of math in the middle to simplify things on the PC end. But I can save all those waveforms and display them fairly quickly. Within about half a second, you'll easily see the picture of what's going on. With my particular POCASA here, I've got 16 channels over here. I've either got them set up as 16 independent channels or 2 banks of 8. I can take these 8 channels here and plug them into one circuit, my known good circuit, my gold circuit, if you will. And I can take the other bank and plug it into my suspect circuit. I can scan all 8 channels, apply pulses to one pin and read 2 other pins, read any combination of 2 pins independently with or without a pulse, swap the ground, swap the signal side, vary the resistance, vary the source resistance, vary the frequency, vary the voltage, and take readings in almost an infinite combination of conditions. Now, you wouldn't want to do that just because it takes so damn long, but you take a bunch of these readings and you put them on a graph and you put them on your screen. And then you take your readings from your suspect circuit and you put them right next to it. Now, I've got, in my software, I've got things that compare picture A to picture A prime, picture B to picture B prime, or waveform A to waveform A prime, B to B prime, whatnot. And in the software, it'll kind of tell you, okay, well, these things are 99% the same. So you can be pretty confident that the circuits are the same. Well, and this is where, the human factor comes in. Maybe when you get down to about 80%, you want to get down there and you want to take a better look at it. So I've got another chunk of software in there that, you put a setting in there, a confidence factor. If you're confident that if 80% of all the test points are the same, then the circuits are identical, well, then that's good for you. Maybe you set it at 50%, so you only have to have 50% of those data points exactly the same, and then you say, I'm good. Or maybe you're paranoid and you set it at 99% or 99.9%. And that's a little much, but you can do that with the software. Let's see what else we got here. Yeah, so I can save. Let's just say I probed this board. Let's just say I took my test points and I probed 200 test points on here. I can save all 200 of those to a reference file, an album, a wave album, if you will. And I can pull up another board and test those same 200 test points. And obviously you keep, well, okay, test point 1 is from here to here, test point 2 is from here to here, test point 3 is from here to here, with the voltage, the frequency, the source resistance, everything else all put in there at the same time. And you scan one board, or you've got your gold sample here, you've scanned it, you know it's good, you know all those readings are good, and then you take your suspect board and you probe all those readings, and then you find that, okay, this reading is bad. Well, what's in between this point and this point? Well, it's that component right there, which that component right there just happens to be a 470K resistor. All right, well, this suspect board showed open, whereas my reference board showed 470K, not quite open, but a slanted line under a certain source resistance condition. Okay, well, then I look at this board underneath the magnifying glass or the microscope, and oh, look at that, there's a bad solder connection there. Bang, I'm done. I didn't have to go through this thing with an ohm meter trying to find 468K ohm or whatnot, or 10 volts here, or 5 volts here, or so many ohms here or whatnot. I just cared about the picture, because Let me erase. Let me do some erasing here. Let's just say I've got 3 boards. Good in the water. There. Should have brought that one up the first time. Let's just say I've got 3 boards here. Those are identical, right? Yeah, whatever. I'll redo this one. Okay, I've got 3 boards. My one scan, test point A, whatnot, on board number 1 looks like this. Test point on board number 2 looks like this. Test point on board number 3 looks like this. Which one's bad? Yeah, that one right there. Who cares how many ohms it is? Who cares how many volts, amps, current, farads, oranges, apples, days of sunlight, whatever. That one is not these two. And that one just happens to be the bad one, and I know these 2 boards work. So I'd go to test point A and B, or whatever I was probing, and I'd figure out what was between those 2 test points. Because in these 2 test points, there's a resistor across there. In this test point, there's a resistor and a capacitor. And in this case, if there was a resistor there and it kind of looks like that, I'd be looking for a cracked solder joint on whatever component was in between those 2. So that's all there is for that. And that's where it comes in useful. Let's see. What else do I got here? Oh, again, on POCASA, on the board here, I've got these 16 channels. I've also got, oh yeah, I've also got a pulse generator in here, like for triggering MOSFETs or transistors. So you got a transistor here. You know what? I can't remember how to draw one. Doesn't matter. So you got a transistor here. I'm going to hook my pulse generator up to the base through a source resistance. And this is in circuit. And so I'm going to apply my test leads are going to go here and here. And with the pulse generator, let's just say it's doing 0 to 2 volts, what have you. At 0 volts, this transistor is probably, let's just say it's an NPN, not pointing, yeah. At 0 volts, this transistor is going to be off for all practical purposes. As long if I'm applying a input wave there across my test points. Down here, it's going to be 0 volts. Up here, it's going to be 2 volts, 0, 2, whatnot. When it's at 0, my scan is going to look like an open. It's going to be a horizontal line. When I get up here to my 2 volts, the scan is going to turn more towards a diode, like this. So basically what you'll see is, as a pulse generator, up, down, say it like, 2 hertz, twice a second. My trace on my screen is going to go open diode, open diode, open diode, open diode, like that. You'll see it do that. And if you test another transistor and it's got the exact same characteristic at the exact same pulse generator voltage at the high point and at the low point, if it's got the same open and the same chair L characteristic, then you know the transistors are probably identical. And then what you want to do is you want to flip that and run the voltage in the test the other way. And then maybe you want to change the voltage level on the pulse generator output to see if the gain, this is basically where the curve tracer thing comes in. You're checking for the HFE. Yeah, the gain of the transistor with a certain voltage at the base or a certain current going through the base. Was that what yeah, that was a pulse generator. And you can also, the pulse generator will also flip relays on and off so you can look at the contacts and see how badly they're bouncing maybe, or if there's a significant resistance across the contacts of a relay. Bunch of different things. You want to fire a triac with it or an SCR. Can't think of what else you'd want to fire with it. Maybe you're checking an op amp, or an IC of some sort. 16-pin IC, and you hook up to pins 9 and 10 and you put a voltage on 3 just to see if anything's going through. Who knows, maybe that chip is blown and it's got a dead short between pin 3 and 9. Who knows? You're checking for all different eventualities quickly is the big thing. In addition to all that, I've got a bunch of analog switches on here that takes it takes all 16 of these pins. Each pin can have the signal, the test signal, a ground, or the pulse generator on it. Each of those 16 pins can have any one of those things on there. Pulse generator doesn't have to be in there anywhere. I can put a ground on pin 1 and then check the signal. Okay, well, let's just draw an 8-pin chip here just for the heck of it. I'm going to check a 555, we'll say. 8-pin chip. Simple enough. 1, 2, 3, 4, 5, 6, 7, 8. Okay. I can put a ground, or I can hook the test point, or 8 of these test points up to my 8 pins of this 555, or whatever have you. It doesn't matter. And let's just say my test sequence says that I'm going to hook ground up to pin 1 first. And then I'm going to take the signal and hook it up to pin 2. And I'm going to put the pulse generator on 3. And then the next time around, I'm going to put the pulse generator on 4, and then on 5, and then on 6, and then 7, and then on 8. And then the next time around, I'm going to put the ground on 1, the signal on 3, and I'm going to pulse gen 2, 4, 5, 6, 7, and 8. And the next time around, the signal is going to go on 4, and my pulse gen is going to be here, 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 and here, here. Cycle all the way through that, and the next time around, I'm going to put the ground on 2, and the signal on 1, and the pulse generator on 3, and so on and so forth down the line. After I get done with all of those iterations, and I don't want to think about how many that is. I mean, you can imagine, you know, you get up to a BGA chip, say like one of those huge 1800 pin flip chip land grid array monkey wrench and FPGA chips, whatnot. And you do this to it, you can imagine how many millions, perhaps billions of test points you'll get. Do you really need that many? Just swap the chip and see what happens. But anyways, all of those 16 signals can have any one of these 3 signals on there. All these 16 pins, these test pins, can have any one of those 3 on there. So you can hook up a ribbon cable to a board and you can check 8 things at a time, or 8 lines at a time, or 16 lines at a time in this case. And in this case here, this is expandable. You can have 1 of each, 16 of each, and I believe my software will go out to 4 or 2 to the 32nd or 2 to the 31st channels, which is roughly 2.5 billion, give or take. So yeah, 2.5 billion wires. I don't think so. Besides that, I don't think they would complete in this lifetime or the next, because we'll be out of oil by then. Anyway, yeah. So hundreds of test points possible in seconds. Let's see, what else do I got here? Pulse gen. Oh yeah, the pulse generator also has a source resistance select, so you can't like smoke the base of a transistor by pumping too much current through it. So I've got a network of 8 resistors to limit that base current, or the current coming out of the pulse generator, much like I do the DDS. Let's see, SRAM for storage, ADCs, op amps, PIC, voltage regulators, switches, op amps, filter caps. That's about it. This particular board has something like 78 fixes on it. Not only bodge wires, but trace cuts, no ball wax. Luckily, I only had 3 of these made. The next run will have all these fixes incorporated into it, plus it'll be quite a bit smaller because I don't have this ATX power supply and all those minimum load resistors hooked up there, so it might be about yay big. Probably going to put a few components on the back to double load it, if you will. And that's about it. 80, 98, 33. Oh, my digital pots are 80, 5204 or AD alpha delta. 5204 or AD 5206. 5204 is a 4-channel digital resistor, SPI controlled. The AD 5206 is a 6-channel digital resistor, again SPI controlled. The ADG 1406 and the 1408 are either 8-channel or 16-channel digital switches with a very low RDS on, about 9, maybe 10 ohms, give or take, and very flat the resistance is the same between all the different channels within a certain really small percentage, versus like the old 4066 or the 4016, you know, where the resistances were all over the place. And that's about it. I've also got a couple of Zeners and a couple of fuses in there in case a guy would want to connect a charged capacitor up to the circuit, which would immediately blow the ADCs out, and not be a good thing. Yep, I'm working on it. The software, I've shown off the software in a couple of my other POCASA videos. I've shown a little bit of the hardware in a couple of the other POCASA videos. So that's where it is. Yeah. Now that's just silly. Whoa, big fella. Come on. There it is. Look, one hand. Yeah, there's some air currents floating around here. Fluorescent light doesn't like the fluorescent light either, apparently. Back here. Oh boy. Right into my face. Enough of that. Toys. Like $10 off a Woot. What do you expect?